Thanks for staying, everyone, although you already had pizza and everything. As Dave mentioned, I work at ING. It's not a subsidiary of King. And I'm going to present, I'm going to talk about some feature importances that are out there and something that we developed in-house at ING that is open source called LOFO, Leave One Feature Out Importance. So yeah, again, feel free to interrupt anytime during the talk, and I think we have time for questions afterwards as well. So feature importances. Have any of you used feature importances before? Okay, cool, good. So feature importances are very important in general. Why? There are two main reasons why I think they're important. The first one is for feature selection, and that's also important for two different reasons. So either you have, let's say, too many features going into your model, and then a lot of them are noisy, so they would dilute the effect of important features that are meaningful, and so they would just introduce noise, like that. So then they're gone. So you want to remove them. And the other reason you want to remove features if there are too many is that you want to make your modeling process faster. So if you have too many features, it takes way too long to train, and that's for no reason if they're not even important. By the way, the microphone's not working, so if you can't hear me, please let me know. The other reason why you want to do feature selection is that you only want to keep meaningful features. Even if there aren't many, you only want to keep those that are actually predictive. Okay, and when I say predictive, it's not just on the training set. So let's say you want a model that would still be valid and meaningful for future data sets in your company or something, then you also want to use features that will continue on being predictive in the future on unseen test sets. And the second reason you want feature importances is to interpret your model. Is your model, which features are your models using? And is that a good thing? So if it's using the right features, and you know from the business that these are the right features, then you can say, okay, my model's reasonable and so on. But if you know that your model is using some other features that you know should not be used, then this is a way to debug your model. For instance, that's just one application of interpretability. And to give an example of that, too many features. This is an example from the developers of LIME. LIME stands for Local Interpretable Model Agnostic Explanations. So this is an example that they give on their blog. So they say, okay, let's say we have some images, and we want to classify whether or not the images contain a frog. So what LIME does is it breaks up the image into interpretable components, like such. And it says, okay, I'm going to make many replicas of this image, let's say 20 replicas. And then in every replica, I'm going to turn off some of the components, meaning that I'm going to erase them, so they're just gray. So then every image would only keep a few of the original pixels or colors or so on. And then it would say, for every one of those images, the grayed out images, I want to predict whether or not there's a frog in it. And it will check which one of those images was most predictive, like most certain of its prediction that there was a frog or there wasn't a frog. And it sees which feature was in, which non-grayed out component was in that image. So if let's say we have this lower, okay, you can't see the bottom, so this component turned out to be the most predictive that there's a frog in it, then you know that something's wrong with your model because it doesn't make any sense, right? But if it says, okay, the eyes actually are telling me that there's a frog in the image, then you can trust your model. But let's talk about interpretability a bit more. So this is a very hot topic these days, and there are so many reasons why it's important. We talked about debugging your model, but there are other things as well. Putting models in production. ING is a bank, okay? It's really important that we know exactly what's going in production because there's so much risk involved and compliance and everything. There's also regulation, and last but not least, ethics. Is your model discriminating on gender, let's say, or something else? So it's really important to understand why your model is making its decisions. And just to show again how hot this topic is, I spent literally 2 minutes on archive. I just typed in interpretability, model interpretability, and I got, I think on half of the page, all of these academic papers on interpretability. So it's a very hot topic. It's highly researched these days. So what we're going to talk about today is what kind of feature importance types there are out there, what kind of classes there are. And specifically, let's say there's global, so for the entire model, versus individualized for every prediction. And then we're going to go through a survey of global importances. And I'm going to explain like where they're used and where they shouldn't be used. And then I'm going to talk about what we developed in ING. So LOFO is leave one feature out importance, and it's fast approximation FLOFO. And then I'm going to briefly talk about individualized importances. We're still working on individualized FLOFO importances. And I'm also going to briefly discuss Shapley values, which are very popular and that I like a lot. So let's start out with classifying feature importance metrics and packages. So as I said, there are global ones and individualized ones. So anything that's individualized can be global because you can sum or average over all the predictions and you get the global one. But individualized is really powerful because for every prediction, you can find out which features contributed to this decision and how. So that's per record or per prediction, per sample, etc. There's the global one for the entire model, and so it's sort of an average over the whole, all of your data samples, and that's important for feature selection. And for both of those classes, you either have implementations or packages that are model specific, so optimized, let's say, for tree models or something, or model agnostic that would work on any model. There are advantages to each one of those two classes. If it's model specific, then maybe in terms of speed, it's optimized and so on. But for model agnostic, it has another benefit, which is that you can use the same metric for any kind of model you want. Yeah, feel free to interrupt at any time. So there's another way you can classify feature importance metrics, which is how they define importance or how they calculate it. So let's take this very simple dummy data set. And we have some features: age, salary, gender, income, the target, and the prediction. So one way to calculate or define importance is to look at the value, so the green here, the value of the prediction, and how it changes with, let's say, changing the features. So how is the prediction on its own changing? And that's the first class, the change in the prediction value. And some packages that do that are Lime and Shapley. Lime we talked about, Shapley I will talk about. And the other way to define importance is to look at the performance of your model. So what is the performance score? What is the accuracy? What is the root mean squared error? Something like that of your model. And that's by comparing the target, so the real value, and your prediction. And how does your performance change by changing, let's say, the features? So these are two different ways to look at importance. Neither is more right than the other, but they're just different ways. They're complementary, let's say. So let's go through some global importance metrics. So the simplest one you can think of, and the favorite one for stakeholders, in my experience, is linear models. Because linear models are very interpretable, very simple. You know exactly what's going on, how each feature is affecting your prediction. You have a complete understanding. So you look at the linear coefficient of every feature. If it's high in absolute value, then it's important. If it's not important, assuming normalized features. But the problem is that many data sets are nonlinear, right? And they have a nonlinear relationship with the target. So linear models are not really enough for many problems. So then we would use more complex models, let's say tree models. And feature importance packages that exist for tree models, there are many of them. Some of the most popular ones are split count. So you look at your decision tree, let's say, or your random forest or so on, and you count how many times a feature appeared on a split. Okay, and this count is the importance of your feature, roughly. But the problem is, and I was just discussing this with someone during the break, is if you have a very granular feature, let's say country, you have more than 200 countries. If you have, it just happens that in the training data, you had a lot of the categories of the country show up. So the model will think that actually it's an important feature because there were so many choices to make and so many different categories and so on. But actually it turns out that country is not important at all. So this metric overestimates the importance of granular features. That's the problem with it. Another importance for tree models is the Gini importance, which calculates the mean decrease in impurity on a split. So every time you split on a feature, what is the, let's say, the decrease in impurity? Impurity can be defined in different ways, but how much sort of performance improvement you get by splitting on this feature. But the problem with this metric is that it overestimates the importance of the features that come at the very end of the tree, because that's where you make the most decrease in impurity. So it allocates a lot of importance to those features. And a third one, which is quite well known, is gain importance, which is very similar to Gini importance, but the impurity is entropy. And another way to say it is it's the average training loss reduction. But this again, so this problem, which actually is a problem for all of these metrics, is that it only looks at the trees and the model and so on in the training phase. So it doesn't. So it's quite specific to the training data set that you're looking at. And if perchance you have features that change distribution with time, they're seasonal, or you want your model or your feature importances to be general for future data sets, then these will be misleading. Okay, sorry, there's a lot of text on the bottom, so I'll just read it out. So the advantages of these metrics are that they're explainable. So you can tell your stakeholder exactly why you think this feature is important. But on the downside, they don't generalize well to unseen test sets. Okay, so let's look at an example. So there's this Kaggle competition that Microsoft proposed, where they give us a data set and they ask us to predict whether a machine will soon be hit with malware. Okay, and one of the features that is in the data set is the operating system version. Now, the thing is that Microsoft wanted something that they can use in the future. So we split the training and test sets out of time. But what happens then is that in your test set, in your validation set, you'll have OS versions that are newer because they're split out of time, and they never appeared in the training set, and vice versa, right? So what happens is that those performance metrics that we just mentioned, they will consider the tree structure in the training phase, and they will learn associations between the OS version and whether or not there will be malware. And this is a very predictive feature, right? Because some OS versions are more prone to bugs than others. So it will learn, okay, this one is more prone to bugs, this one is not, etc. And then you'll give it the validation set with completely new versions, and it won't know what to do, or it will make the wrong kinds of deductions about them. So I got this plot from a Kaggle kernel where they use light GBM, and I think they use the gain importance. And it turns out for them that the OS version is the 6th most important feature. Okay, and I'm going to show later how we can solve this problem. So before I do that, some more global importance metrics. There's the permutation importance that doesn't have this problem. So what this one does is that it takes a model that's already been trained on a training set, and it takes a validation set, and it says, I'm going to go over one feature at a time, and every time for this feature, I'm going to permute all the values, and I'm going to evaluate the performance of the model, and I'm going to see how much it changed. If it didn't change at all, then the permutation had no effect, and therefore this feature was actually not important. Okay, and if it changed a lot, then actually this feature was important. This is a really cool metric, and it does generalize well, but it could be even better. Spoiler alert. It was not very well timed. Another package is called Baruta, which is really interesting. It's only implemented in R, but okay, this is a bit complex, so I hope you can follow through. Okay, so what it does is that you have your data set, you have all the original features, okay? You make copies of all of your features. These are called shadow features. And then you permute all of your shadow features. You keep your original features the same, you permute all of their duplicates. Okay, and then you take whatever performance metric, whatever importance metric you want, and you evaluate, so this is the training set, you evaluate the importance of all of those features, the original ones and the duplicates. Okay, now you have importances for each feature. Then you take the maximum of maximum importance of all the shadow features, and this is now your threshold. So any original feature that has an importance much, much higher than this maximum importance of the shadow feature, is an important feature. Anything with a much lower importance is not an important feature. And anything in the middle, we can't label it so far, so we keep it on hold. We take out the labeled features, and we repeat the process. Okay? Any questions? Yes?
Do you train on both shadow features and normal features, or do you train separate models, one on the normal features, one on the shadow?
No, the same model on both all features, indeed. And yeah, your assumption is that the shadow features shouldn't be important at all. So the maximum importance there is a good threshold for like unimportant features. Yeah.
Does this method normally converge?
No, not always. So sometimes it converges, sometimes it doesn't. But I think what they do is that they say, we'll run it for 100 iterations. If it hasn't finished by then, we'll stop. Yeah. Yes?
For the shadow features, do you permute the features on each row, or do you permute them for all rows at the same time?
You permute per column. So the feature itself, you permute its values.
Oh, okay.
Yeah. Okay, cool. Yeah, so on the plus side, this is cool because you can use whatever importance metric you want. On the downside, it's only implemented right now for feature selection, so it iterates and it does these decisions on its own. And it's a bit slow because every time it retrains and so on. And the last one I'm going to talk about is recursive feature elimination. So what this one does is it goes through every feature at a time. It leaves this feature out. It retrains the model completely, and it sees what is the change in the performance. Then it says, okay, these are the importances based on the change in the performance of the model. I'm going to take the bottom n features, so the n least important ones. N is by default 1, but you could set it to whatever you want. And I'm going to remove those features, and I'm going to repeat. Okay, so this is really cool because it retrains every time. So the model is completely oblivious to the feature. So it's a good metric to measure the direct impact of the feature. But also it's only implemented for feature selection. So it keeps iterating on its own. And it allows you to remove more than one feature at a time, which is not good. It uses flawed performance metrics to evaluate the importance at every iteration. So some of the ones we've already seen. And it's slow because it retrains. So, leave one feature out importance. This is what we developed. In a nutshell, it's also a global importance metric. What it does is it calculates the average difference in the cross-validated performance on validation sets upon leaving one feature out at a time. So I'm going to repeat this, but anyway, it combines ideas from what we've seen. It still has some problems, but I'll also go through that. So it goes over every feature at a time, removes it, completely retrains, and then not only does it look at the change in the performance, but it also does this over different folds in order to ensure that it's actually doing it fairly, there's not much randomness, and so on. And the power in that is also that you get to choose what is your validation scheme. So if you are optimizing for having a model that generalizes well to unseen test sets, then you should use some time series split validator, for example. It depends on your use case. But it's up to you. So let's first, I'll talk a bit more about that. But let's first go through the pseudocode. So this is the algorithm. You give it whatever model you want. It's not trained yet. It's just the model with its hyperparameters and so on. Whatever performance metric you want, and the validation scheme that you want. And at the beginning, what it says is, I'm going to keep all the features in with their original values and everything. And I'm going to get the CV performance scores on all the folds. So the score is based on whatever performance metric you choose of this model of your choice. So you get the initial performance scores. And then you loop over the features. For every feature, you remove it from the data set. You retrain the model on the new subset of features. You get the new performance scores, and the importance of this feature is the difference over, it's the mean of the difference over all the folds. Okay, so this has some pluses and minuses as well. So on the bright side, it's model, metric, and validation scheme agnostic. And if you don't give it a model at all, it defaults to light GBM, which is a really cool tree model that handles categorical features. It's good because it directly measures, it's pragmatic basically. It's not like it doesn't have foundations in theory or anything, but it's heuristic, but it directly measures the impact on the performance, which is really like in data science what we want. And you can choose whatever validation scheme that suits your use case. And it generalizes well to unseen test sets if you use, let's say, time series splits. So seasonal features stop being misleading. On the downside, it's quite slow because at every iteration you have to retrain. This is the package, by the way. It's open source. It's on GitHub. It's called, you can pip install it as well. It's called LOFO-importance. So going back to the example, oh, I don't think I'm connected, but I have it open. Yes, please.
So it's very good that you explained so many models here. But can you have any tips like which model should be offered, which type of use case, or like you said, the other one you should use for time series?
Which model or which validation scheme?
Which validation schemes?
It depends. Like if you want, if you don't care about the order, you can use shuffling validation schemes. I think there's, yeah. I mean,
It looks like really all the models are good, but which one you apply for your use case? It's really tough, isn't it? It's the same like which regression model or linear or regression. Same way, which type of validation you would like to use to bring the features out?
Yeah, it really depends. Like, for example, the reason why we developed LOFO was because we had seasonal features, and none of the feature importance packages out there were solving our problems. So we developed this, but then we said, you know, like, yeah, you could use time series splits, but you don't have to. It depends on the use case and whatever is your use case. So you have to think of what your model is designed to be like, right? Like, is it like in finance? Of course, you care a lot about the time component, but for image classification, you really don't. So you could completely shuffle your samples if you want. So you really have to think about your own use case. There's this scikit-learn page with like more than 20 validation schemes. Yeah, you can look at all of them over there and see whatever fits most. Yes.
Is it Python or R language that LOFO imported quite recently?
Python, yeah. Okay. So I hope this is open, actually. No, it's not. Okay. Maybe it's here. No. Okay, I'll just be 1 second, sorry. Okay, so going back to the example of the Microsoft Kaggle competition, we had that OS version feature that was quite misleading. So we have our own kernel on Kaggle that looks at this problem, which doesn't show. But, okay, I'll probably come back to it later. But the point is we ran LOFO on this problem. We tried to look at the feature importances there, and what happened is LOFO figured out that not only is it not an important feature, but it's actually a harmful feature. So it gave it negative importance, and it's like a warning to not use this feature in case you're splitting by time. Yeah, I also wanted to show you the visualization.
I've got a Wi-Fi password.
Yeah? Oh, there it is. Go ahead.
There's a Wi-Fi password.
Okay. It looked like it opened, thank you. Okay, so here it is. So this is LOFO. The way you can call it is you can give it a model or not. If you don't, like here we didn't give it the name of the model we want to use. It defaults to LightGBM. We give it the data set, which it will split into training and validation sets. The features, the target, and the validation scheme, which is here k-fold. and the performance metric, which is here the area under the curve. And we run this get importance function. And what you get is for every feature, the mean of the importance over the folds and the standard deviation. And here is the visualization. So the end of the bar here is the mean of the importance, and the black bar here is the standard deviation around it. And you can see here on the bottom that the OS version is actually the least important feature, and it's actually like a harmful feature to have. So it has negative or red importance.
They look like outliers, right?
What do you mean?
Outliers, it's like not coming.
Oh, yeah, I guess.
It don't come on the means.
It's a UX decision. We didn't have any UXers on the project. So the problem with LOFO is that it's slow because it retrains. And it can take actually quite a lot of hours if you have large data sets with a lot of features and a lot of data samples. So we made a fast approximation of it, which is called Fast LOFO or FLOFO. It's also global. And what it does is it takes in an already trained model, so it does absolutely no retraining, a performance metric of your choice, and a validation set. And what it does is that it simulates missing features, so leaving one out, let's say, on the validation set, by permuting the feature values in the validation set, which is exactly equal to permutation importance, right? So yes and no. So it's a variant of it. So what FLOFO does, which is different than permutation importance, is that it doesn't just completely randomly shuffle the values of the feature, but let's look at this dummy data set again. So let's say we want the importance of salary. You have those values inside. You don't completely randomly shuffle. You just you choose two other features at random in the data set, like gender and income, let's say. You group by values of gender and income, and you permute salary within those groups. So here we have this group of females that earn 45K, and we only permute values of salary within this group. And then you see for this permuted data set with salary permuted, what is the change in the performance of the data set, and you calculate the difference. But then you might think, okay, but this choice of gender and income, okay, it was random, but could have been very biased. Like, what if they're very highly correlated to salary or very uncorrelated? And when you want the importance of age, you find something that's very different. That's like, if this time it was correlated, next time it's uncorrelated. It's not fair. So that's why we make this choice of two random features at least 10 times. So this time we chose gender income, next time we'll choose age, gender, third time we'll use something else, and every time we permute and we look at the change in importance, and then we get the average change of performance over all these n times. So just to give a bit of intuition on why this is better than randomly permuting the entire column. Let's say you have a pre-trained model, it's linear, and this is the linear model that you got. You're trying to predict the rent out of all of these features, and this is what you get. So by using FLOFO importance, what happens is actually, I don't know if you noticed, but salary and income are exact duplicates. So what happens is that if you're grouping by income, then permuting salary values within groups of income will not permute salary at all. So you'll get exactly the same column and exactly the same predictions and exactly the same performance. So FLOFO, since it calculates the difference in the performance, it will say that, okay, the importance of this feature salary is actually 0. Whereas if you had permuted the entire column, it would have given a positive importance. This is a bit about the intuition. And now we do this again. There's a lot of different applications to feature importances in general. And here we show how we used LOFO and FLOFO to do adversarial validation. So for example, let's say you know that your data set has seasonal features, or you want to make sure that it doesn't, let's say. So you want to check for that. Then what you can do is you have the training set and the validation set, and you want to see whether a model can predict whether a sample comes from the training set or it comes from the validation set. If the feature has different distributions, then the model will be able to tell, okay, I used this feature to tell whether it comes from the training set or the validation set. So we did this on another Kaggle competition, which is Pet Finder Adoption Prediction. And we ran LOFO and FLOFO on it. And we found very similar results, which are that the most predictive features to predict whether a sample comes from the training or the validation set are state and description length and fee and breed to, for instance. But that's just an example. We don't have to go into the details now. Something else we're working on, but it's not finished yet, is, okay, we've seen a lot of global feature importance packages, but what if we really want to interpret every prediction? So what features affected every prediction? So these are individualized importance metrics. And they're really important for interpretability, so we wanted to make a variant of FLOFO for that as well. So let's say we're back to this data set. We want to predict the rent. So we have the target, we have our model, we have a prediction from the model. And what we want from individualized importance metrics is that we go through every row at a time, so every prediction, and we look at the difference in the performance of the model for every prediction. Okay, and once we have the, let's say, the permuted data set, so because of FLOFO, then we can see what is the change in the performance, and that is per row. We want that per row. So how do we do it? We have the target and the initial prediction with the initial values of the features unpermuted. And we want to, let's say our performance metric has been chosen as RMSE. So we want to calculate the RMSE per row, the original one before permuting. So we just have one value for the target and one value for the prediction, whereas RMSE or any performance metric expects a vector, two vectors of values which it will run the metric on, right? So what we do is we synthesize vectors of length n from this first value and the second value. So we duplicate 551 10 times, we replicate 560 10 times, we get these two synthetic vectors and we put them through the performance metric. And we get the original performance of the unpermuted record. Then what we do is we say, okay, now I want to run FLOFO, so I'll run it for 10 times. Each of these 10 times, I'm going to choose two features out of the data set. I'm going to group by them, and I'm going to permute my feature of interest within those groups. So you get 10 predictions out of these 10 permutations. And now again, we want to run our performance metric on the target versus all these predictions. So we synthesize a vector, which is the target replicated 10 times, 551 10 times, and you have these 10 predictions, and you put these two vectors into the RMSE performance metric, and you get the new performance vector. And then to get the importance per record, we take the mean out of the difference of the RMSE, sorry, not the mean, the difference of the RMSE of before and after, unpermuted versus permuted. So we're still working on that, and we also want to develop a visualization for that. But just before finishing, I'm going to talk about another individualized importance metric that's quite popular these days and is very cool, called Shapley values. So what Shapley values does is it's called an additive feature attribution method, which means that the prediction value is equal to the sum of the feature importances. So this one actually, as opposed to what we were doing, we were always looking at the change in the performance of the model. This one looks at the change in the value of the prediction. So it looks at the change in the value, and every feature attribution, if you sum that, you get the actual prediction value. Shapley values have foundations in theory, in game theory specifically, and they're really cool, except they're really slow. So I can explain the equation if you guys want. I don't know if you want. Okay, I'm gonna explain it. And then, but yeah, it's quite slow. So there's a lot of packages out there now that optimize Shapley values for specific models. Like you have tree SHAP, you have kernel SHAP, you have deep SHAP. For neural nets, everyone is optimized in terms of speed for different models. And I'm not going to explain everything, but just to get an idea, what it does is it takes an already trained model. The trained model is called F, And it says, okay, I want to see the impact of my feature I on the output of the model. So what I'm going to do is I'm going to take all my subsets S of the n features. So not just what I was doing was I was taking all of the features and just leave one out. What they do is they take all of the features, they leave one out, and then they take all the features minus one and leave one out, and then all the features minus one, leave one out, etc. So they take all the subsets of the features without this feature, and then they see the effect of the model on adding this feature to the subset versus not adding this feature to the subset. And they look at how the prediction itself changes with or without this feature. And that's just a counting factor we don't have to go into, and this we also don't have to go into. But yeah, so that's Shapley values, and to show you what they output out of it, this is just one of their many really cool visualizations. So this plot here is from the paper of the developers of the Shapley values version optimized for trees. What they're trying to do is they're trying to predict the survival rate on 20-year mortality data. So the higher the SHAP value on the x-axis, the higher the log odds of death for the person. And on this visualization, every dot you see is a record, so it's a person, okay? And what they're doing is they're saying, they calculated SHAP values with the equation we just saw, and the colors encode the sort of range of values for this feature. So pink is high and blue is low. So what this means, for example, for the first feature, age, is that high values of age are associated with higher log odds of death, whereas low values of age are associated with lower log odds of death. Whereas if you look at the third feature, systolic blood pressure, you can see that high values of that is associated with high log odds of death. However, low values of systolic BP are not associated with low values of log odds of death, because you don't have this line going to the left side. So it's very interpretable. There's many applications to even this visualization. You can even cluster records by their importances. So it's really cool. But yeah, we're also like in the process of doing something similar to FLOFO individualized importances. So just to sum up, we've seen that feature importances are crucial. There are two main applications, feature selection and interpretability. You can classify feature importances into different classes, either global for the whole model or individualized per prediction. You can either look at the change in the model performance or the change in the model output. LOFO, leave one feature out importance, is model, metric, and validation scheme agnostic. However, it's slow. There's its fast approximation, FLOFO, which is a smarter version of the permutation importance, and individualized versions are coming soon. So please try it out. It's pip install LOFO-importance. Thank you.